Eating plants and eating animals, two kinds of diets that require very different behaviours. Now, strong dependence on these different kinds of foods and associated behaviours over many generations can help influence the evolution of the skull. And this means there's some key differences often seen between the skulls of plant-eating and meat-eating animals. So in this episode, by popular demand, we're going to be comparing the skulls of herbivores and carnivores. I'm Dr. Rex, welcome to the Skullywag Lab where I present the bare bones fundamentals of skull science. Today, we're going to be comparing the skulls of carnivores with the skulls of herbivores. But there's one little thing I need to mention first before we really get into it, and that is that these diet categorizations often aren't as clear cut as we would like them to be. Some carnivores eat vegetation occasionally, and some herbivores eat animal material occasionally. It just depends on what their body needs at a given time and what opportunities present themselves. Diet should probably instead be interpreted as something of a continuum of food proportions, with certain species having a stronger dependence on specific materials that are found in nature. The skull anatomy of different animals has been shaped by dietary demands in their evolutionary history, and whichever foods have been more important for the survival of their ancestors. So there are some well-known, clear-cut differences in the skulls of animals that rely more on catching and feeding on prey, versus animals that spend a lot of their days plucking and chewing on vegetation. This episode's going to be focusing more on mammals because they have more obvious differences. And this stems from the high degree of specialization in their teeth, something known as heterodonty. And that's where we're going to start. We're going to start with the teeth. The teeth are often the first point of contact with food and, at least in mammals, a major site of physical breakdown. Incisors tend to be used for grasping or grooming, canines are often used for many things, some more violent than others. Premolars tend to be used more for slicing, and molars are usually better for grinding. But none of these are really rigid tasks for each tooth type. For example, the premolars of giant pandas have become better shaped for crushing and are referred to as malariform. Yeah. And the lower molar of carnivorans like dogs and cats serves as one of their big slicing carnassial teeth. The incisors tend to be more general, multi-purpose tools, but they can even be absent to varying degrees in many herbivores. All upper incisors are missing in deer and cows. All lower incisors are missing in elephants. And all incisors are completely gone in others, both living and extinct. Carnivores instead tend to have anterior teeth better suited to grip onto and hold prey in place, and also to tear through tissues like hide or pull away chunks of meat. In herbivores, there isn't really much need for securing food too vigorously, so their front teeth, if they're present at all, are better for selecting, plucking, or tugging at vegetation. Many herbivores actually have canines, but these are usually small, except for some crazy deer species, and camels have surprisingly big ones too. But one common pattern seen across many different groups of mammals is that carnivores tend to have more of their cheek teeth, that's the premolars and molars, better suited for slicing behaviours, whereas herbivores tend to have more of those cheek teeth better suited for grinding behaviours. This deer skull has an entire tooth row of grinding premolars and molars, while the majority of the fox dental arcade is better for slicing. Foxes and other canids only have a very small area for crushing and grinding at the back, while cats have pretty much no space for grinding anything. And while marsupial heads might often look similar to foxes and deer on the outside, their skulls are pretty unique underneath it all. Yet we still see a similar pattern of grinding versus slicing teeth when comparing a herbivorous kangaroo with a carnivorous quoll. Now let's move on to the muscles. Remember, there's two main muscle complexes that are used during biting. These are the temporalis complex and the masseter complex. But there's another really important muscle used during chewing called the medial pterygoid. This muscle originates from the base of the skull behind the palate and inserts on the inside surface of the mandibular angle there. This is the muscle you use a lot when you're moving your jaw from side to side. Now there's one big difference in the muscles of carnivores and herbivores, and this comes down to the proportional sizes of these muscles. Carnivores have a relatively larger temporalis complex, while herbivores have a much more developed masseter complex and larger medial pterygoids. But why do we see this pattern? I mean, at first glance it doesn't really make a whole lot of sense. The masseter complex is further forward on the face, and this means that it offers more leverage and can help produce a harder bite. So why don't carnivores have huge masseters to help them bite harder? Well, this mostly comes down to the orientation of the muscle vectors and their role in maintaining the balance and integrity of the jaw joint. The directions of muscle vectors are essentially defined by the average direction of all the muscle fibers. In the case of the temporalis, the average direction of all the muscle fibers is pulling the jaw upwards and backwards. But in the masseter complex, the orientation is a little different, and the average force vector instead pulls the jaw closed in an upwards and forwards motion. To understand why this matters, I'm going to introduce you to a friend of mine. This is Paco, and Paco is a year old this month, and he likes to play a lot. But there's one game he likes more than any other: tug of war. Paco will pull hard as he can against any piece of rope or cloth you dangle in front of him. This is a behaviour very common in carnivores that subdue struggling prey and pull parts of their kill away during feeding. This means the jaw needs to resist against the forces pulling the jaw forwards. Otherwise, the jaw could dislocate and injure the animal. And an injured jaw means no more eating. So there's an enormously high selective pressure placed on keeping that jaw joint safe. Now, if you look at the vectors of the muscles, the temporalis vector runs in the opposite direction to the forces pulling at the mandible during these kinds of behaviours. This means that the temporalis is just better suited to assist in keeping the jaw joint from dislocating during pulling actions. It's almost like Paco is having a mini game of tug of war in his head while playing tug of war.
Awesome.
But the masseter complex runs in the opposite direction, so if carnivores relied more on these muscles, they'd just be helping pull the jaw forwards and out of the jaw joint. Now, because herbivores don't need such vigorous tugging actions to get at their food, they can afford to increase the size of their masseter complex, which gives them better leverage for grinding up foods, which is something they do all day. The large medial pterygoid works counter to the masseter muscles in moving the jaw from side to side, and these are absolutely massive in horses. You can see here these large medial pterygoids in kangaroos hang out in this pocket of the mandible. And this brings us to the differences in the skull itself. The motions of the jaw in herbivores can be highly complex. This requires greater mobility of the jaw joint. In comparison, the jaw motions of carnivores can be fairly uniform, mostly involving scissor-like actions to grab and slice things. So while carnivores often have a very tight jaw joint that's almost hinge-like, the joint is much more open and flatter in herbivores. Another feature frequently seen in herbivores is this large gap here between the teeth called a diastema. Now, it's certainly not a feature of all herbivores, but it is more common in these kinds of taller, larger, longer face species. The presence of a large diastema doesn't really have just one strict cause, but mostly comes down to a few things. Firstly, oftentimes herbivores have fewer premolars, and their canines can be much smaller or even absent as well. The loss of these teeth can extend the gap between the front teeth and the cheek teeth. Both premolars and canines are useful for gripping and tearing actions, so we rarely see loss of these teeth in carnivores. Secondly, a lot of the time there's negative allometry of the teeth, which means that larger species have relatively smaller teeth for their size. This can also increase the gap between the front teeth, which obviously need to be at the front of the skull, and the grinding cheek teeth, which have better leverage further back in the jaw. And thirdly, in many larger herbivores, the front of the mouth or premaxillary region is extended forward. This would increase the length of the diastema and can help with various things like improving reach or cropping capacity or selecting nice bits of vegetation. So there's a few reasons why that long gap exists in herbivores. Now finally, let's take a look at the height of the jaw joint relative to the tooth row. This part of the jaw joint on the mandible is called the condyle, and there's been a lot of discussion over why these tend to be positioned more in line with the tooth row in carnivores, but higher than the tooth row in herbivores. A popular reason is that a lower condyle increases how wide an animal's jaw can open, also known as their gape. This is because it reduces the amount of stretching the jaw muscles need to do while opening the mouth. Since herbivores don't really need wider gapes, they don't really need such low condyles. Another reason is that deeper condyles also offer more room for enlarged masseter and medial pterygoid muscles. But I think there might be one other reason which hasn't really been discussed very much, if at all. And that is a higher condyle actually reduces the movement of the jaw joint while maximizing the movement across the grinding teeth. I'll show you why I think this is. Let's say you have a jaw joint that's in line with a tooth row, like we see in many carnivores. Well, this is a good configuration for scissor-like slicing actions of the mandible, but there's very little movement in any other axis. While the jaw can move up and down, and even left and right a little bit, there's almost no ability to rotate the jaw along that additional axis. But look what happens when we increase the height of the condyle. This provides a broader range of motion of an entirely different axis of rotation, which happens to rotate laterally across the grinding teeth. This would mean that a deeper jaw allows a more dynamic range of motion, while reducing the movements of the jaw joint itself. This is especially true in many herbivores that have unfused dentaries that can swivel more independently while chewing. So, there you have it. We've covered a whole range of interesting trade-offs going on in the skulls of carnivores and herbivores. This includes trade-offs of slicing versus grinding actions of the teeth, trade-offs of dominant muscle complexes owing to the directions of the vectors and their influence on jaw joint integrity. We're talking trade-offs between gape and mechanical efficiency, and there's a whole range of others as well. And it's this constant shifting of the importance of these different trade-offs and the outcomes on the function of the skull that have helped determine the vast diversity of the skulls of animals we see around today. If you've appreciated this content, leave a like and subscribe, and I'll see you in the next video.